And so there's additional information about short wavelength land motion at these benchmarks. So today in this talk, I'll try to give an overview of some of the different applications that we've applied these historic geodetic data, and then talk a bit about the ways, the sort of data that exist and some of the challenges for others to use those going forward. So again, a lot of our interest has been in observing vertical deformation rates and then relating those observations to things that we care about, like the extent of coupling on the subduction interface, as shown schematically here for Cascadia. And then also understanding detailed patterns of local land motion. Regional land motion is important for understanding future sea level rise impacts, as well as patterns of tsunami inundation. And I'll show you one little example of some promise for using these archival data to study early tsunamis. We at Cascadia, one of the things that we did was, in addition to the kind of continuous time series of sea level data that are available from NOAA on websites and things, we went back to the archives and found months of older data that were not available anywhere else, and digitized hourly records into monthly means that are plotted here. And by putting in those old data and making, also finding the leveling history for the tide gauges, we could tie those old observations at some of these shorter duration tide gauges into the same vertical datum. We also corrected errors caused by benchmark instability in these more continuous parts of the time series. And so there were a lot of good outcomes that came from these archive data. And we can get a better rate over the kind of century time scales by adding in these old data in the right locations. Another example, we also, there are many more sites where NOAA collected kind of campaign style tide gauge data to densify their understanding of the tides over the region. And so at Florence, Oregon, for example, at the Siuslaw estuary, there was a year of data collected in the 30s, a month in the 70s, and then we went back in the late 2000s and installed our own tide gauges at the same locations, recovered the benchmarks, and were able to tie our modern observations in and start to work towards getting time series of relative sea level rise and vertical deformation at some additional sites. So I think there's a lot of promise for more of that kind of work in the future. And one of the main motivations for us was trying to understand extent of coupling or slip deficit rates on the subduction interface and how that relates to seismic hazard. So we modeled the observed vertical land motions and over the region, and then related that to coupling on the interface. These data have also been used by others, like this McCaffrey and others paper, in integrating with space geodetic deformation rates as well. At least at that time, the vertical deformation rates that we could get from these long historic records was better than the precisions of space geodetic verticals. And one of the things that we can start to, questions we can start to answer with these long time series that extend in some cases up to a century or more is, how steady are these differences in vertical deformation rates. So this is an example from the Strait of Juan de Fuca. Here's the long-running Seattle tide gauge that's located about as far down dip on the Cascadia subduction zone as any tide gauge. and then comparing it to the Nia Bay tide gauge that has a very negative rate of relative sea level change through time. And so these are the monthly mean time series from those tide gauges. And if we difference them, most of the oceanographic signal is shared and cancels out. So we're basically left with a time series of relative vertical deformation between those two sites. And this yellow line is a quadratic model fit to that time series. And you can see that over that nearly century timescale, there's been very little change in the vertical deformation rate. So I think that there's opportunities to test these sort of questions in a way that won't be possible with space geodetic data for decades to come. Another application that we came out of some of our work is trying to understand the stability of the tide gauges. And so this is an example from the Astoria tide gauge at the mouth of the Columbia River, time series of local leveling between pretty closely spaced benchmarks, probably within a kilometer of each other. And you can see that among these three benchmarks, they're all moving relative to each other. We interpret Tidal 7 as being the most stable one, but these other two were used to establish that vertical datum at the tide gauge, and the record was contaminated by these trends. So there's a pretty large gradients in local deformation rates that aren't necessarily easy to recognize. Another case where we have instability in part of the tide gauge time series that NOAA distributes, and you can see that these time series of leveling between these benchmarks, not only is there a major difference in the rate of motion, but it is also changing through time. So as we look forward to the future and development of these more precise INSAR time series, being able to compare back to what different places were doing in the pre-INSAR GNSS era is going to be important for understanding some of these local deformation processes. And similar to the historic data where we see these short wavelength variations in vertical land motion, some of the preliminary observations from INSAR show similar scales of gradients that are affecting the coastline and sea level impacts. Another pretty cool example is looking at the tide gauge time series to extend our understanding of episodic tremor and slip events going back in the pre-GNSS era. And so this is some work by Sequoia Alba and Ray and others. And we can also ask questions about how over many of these ETS cycles, how is there a net accumulation of strain or is all of the kind of inter event strain being released in each ETS event? And we find that there is a persistent, fairly subtle signal of long-term over a period of 10 decades that is persistent on the eastern ends of some of these leveling profiles that can be interpreted as some amount of net strain accumulation over multiple ETS cycles. Some work that we did with, led by Randy Krogstad at U of O. And one other kind of cool example out of my expertise, but that there, in addition to the kind of numerical average data that NOAA distributes, even in the very old data from the 1800s, in many cases, the data were recorded at tide gauges by these merograms that are similar to a seismogram. And you can see on this trace from 1868 that the tide gauge at Astoria recorded incoming tsunami waves from an earthquake on the Chilean subduction zone. So I think I don't know to what extent these data have been exploited for this purpose, but it seems like there are certainly opportunities to understand these like pre-seismic recorded earthquakes. So briefly about the kinds of data that we have at U of O. Ray scanned boxes and boxes of data that were a subset of the NOAA information for the tide gauges in the Pacific Northwest at Cascadia. And so now he's moving to emeritus status and has had to downsize his office space. And so has scanned most of these records, but they're just in kind of image format. And you can see that the data structure is not very friendly in general. This is an example of a benchmark data sheet. And so we digitized a lot of this data ourselves, but keeping a record of the original data, I think, would be valuable for future people. And here's an example of some of those hourly water levels that we digitized for some of the Oregon gauges. This is from Bremerton, Washington, for example. So there's a large volume of data, and it's kind of tricky because the data is clearly owned and produced by these federal agencies. But there's, as shown by this diagram, there's a pretty complicated set of different archives, and many of the data are not easily findable. And so people like Ray and also this group at Portland State University and Cal Poly have collected subsets of the data that are really valuable, but if there's not a way to make the data findable and accessible by others, then we may lose those custom data sets. So I think there's a lot of opportunities with new technologies, and there's clearly people working on this topic, but I think there's great potential to push these sort of approaches for studying subduction zones in Cascadia and elsewhere around the world. And I think I'm probably used up my time, so I will move on to showing these conclusions, and if there's any time, I'm happy to take questions. Thanks.
Thank you very much. We really appreciate your talk. We have a few minutes for questions, so just a reminder to everyone that the Q&A feature or the chat are both available if you have any questions. I'll give a few minutes for people to type those up, and then we can move on to our next speaker. Okay, if we don't have any questions right now, we'll also have time at the end of this panelist session to take questions for all of the speakers. So without further ado, I think we're going to move on to Dr. Ray Cakir. Ray Cakir is a senior scientist working for Washington Geological Survey since 2006. He is a geophysicist, seismologist, and earthquake risk analyst, and his current focus is building a subsurface database in Washington. Thank you very much for joining us, and without further ado, the floor is yours.
Hi, everyone. This is, again, interesting database. I just thought that the community can benefit from that. This is a Washington Geological Survey subsurface database. It started with because Geological Survey, Washington Geological Survey is tasked by state law to collect geotech reports and subsurface information for the support of geologic hazard identification in Washington State. So initially we started with the for landslide emphasis, but then expanded to other types of subsurface database too. So this currently we are running this subsurface database building in the subsurface database in Washington is by the funding mechanism and light funding mechanism from USGS is the data preservation funding. And so we are also building up at least a minimum 5,000 boreholes per year to online and available to as a public on the our portal. So what is the source of the subsurface database? It's of course the reports on the shelves, and they are stuck somewhere else, and then it was done, for example, and then every subsurface database needed in any engineering cases or water wells, and so subsurface borehole data, including logs of borings and test pits, are vital for geotechnical analysis and civil engineering applications. But I'm going to present here the process and challenges, and then how do we manage, and then how do we put them online. So as a brief explanation. So the sharing geotechnical reports and subsurface information in Washington Geological Survey through the portal. So our goal is from this reports one time used in the past for geotechnical projects or other types of the public utility or road construction projects. So bringing them to the to our database starts with the communicating with the sources, and then they are usually is the PUDs, public utility departments, public works, and Department of Transportation and such. So this is our site for them. And first thing is the coordination meetings and explaining how it's useful for their cases. Most of the, for example, city halls or public utility offices, and they don't have personnel to stock these, or they already scan them and then put them on as the PDF files and stored in their database. So we collect them either in the report case in the boxes, they transfer to our office, and we scan them and make them PDF first, or we give them a site they can upload, as you can see is the document submission site. And then our contact person for the geologic planning liaison as Tricia Sears. So communicates and coordinates with those communities or the counties. So it's easy as soon as they are PDF, and then they can upload from, the counties can upload from this site, and then as soon as they upload, and it is in our folders, and we just organize them and then start the process. So here's the okay, here's the type of the report. You can see the report comes with the location map, and then a bunch of borehole test pits or water wells in it. So first we locate the place and georeference the map, and then extract the location of those, so those boreholes. And then enter the descriptions if there is exist, and then other tests like geotechnical tests, SPTs, then file descriptions, and also other types of the subsurface data, such as hydro, and then if there is a bedrock information, and then or any borehole information recorded. So here's the workflow, how we do. So the data resources, as I said, county, city offices, public works departments, and Department of Transportation as examples. And then if they have PDFs and they come through our website, and they can upload immediately. And then if they are in the paper form, we pick them up or they send us, and then we scan and then convert them to text form because they are in image form. And then we organize and enter all the data in the GIS database. Currently we use ArcGIS Pro environment. So it goes through from the georeferencing to all the way to the portal in that environment. So what we can do from this, and then we so far tested like map service, like a geology portal. We in the portal we make them public as soon as we edit and extract the information and ready to go to the public. It goes to portal, and then it's downloadable. And then we do some derivative products like I will talk about in a minute. So here's the subsurface database structure. It's simply a borehole information is the purple color is the documents, and borehole information is the main information. And then also there are documents without the boreholes, and if they are critical for landslide and other geological hazard, we separate them in case of the use in future. And then so they are the boreholes and document IDs is relational database, and then from the borehole IDs we can connect them to hydrologic layer. There are comments from the drillers, and bedrock information, and then test institute test results. They are the SPT, standard penetration tests, or CPT, column penetration tests. And so we do have those. We enter them, and also layer data. The layer data means is the description of the borehole drilled. Description means is the layers descriptions. So if there is a geologic unit, so we enter, and then they are all connected, all the sub information. So it's a relational and ever-growing data. So if the community says they are interested in the further information, must be digital, and then so we can have one of these connections. Another attribute table can come up. So it's a flexible structure, a schema. So here's the current map from my desktop. And so as October, like yesterday, and we do have 118,992 holes. They are boreholes, test pits, monitoring wells, etc. So some of those I highlighted. For example, borehole depth is greater than 1,000 feet, is 392 of them is available on public right now. And then some of them has like 3-4 of them is going very deep, like 1,000 to 9,000 feet. So it's maybe they are critical for the bedrock and other information. So they are rare data, so we save them and make them public. So it's the depth between 500 and 99, so I'm just classifying that. So it's, if we look at borehole depth is greater than 100 feet, is 15,000 of them. So what is that? What that means is the where the spatially distributed is mostly in the I-5 corridor. However, they are the major cities in the I-5 corridor is vulnerable to the earthquakes. And so this might be a good data for like VS30 and soil amplification data. If we do subduction earthquake, and then so we encounter some of the like deep boreholes, depth to bedrock is important for the sediment thickness and sediment response. And then the other one is the shallow response. They are critical for high-rise buildings and like 1 to 3 story buildings type, and like residential buildings. So most of those in the I-5 corridor and also in the Eastern Washington area. So this is to me is critical data. So we put them on the portal, our portal, Geology Information Portal of Washington State. And so it's public and it's downloadable. And here's the links, or you can do a search. And then here's some other types of subsurface database can be used. The derivative maps we can get, liquefaction susceptibility, one of them, and geologic mapping, another, and the cross sections in urban areas, and we do have quite a bit data now. And then depth to bedrock models, as I said, and 3D geology models. Recently, we developed the aggregate availability maps and groundwater availability and quality data. And so these are can be generated more, and maybe climate change might enter in this, and some other geothermal favorability maps and those kind of information. But currently, geotechnical engineering firms, before going to field, they check this database first and make sure they don't duplicate the same or get the information about the site earlier, and design their work. So here's some examples. And then also we do have geophysical and subsurface data together. So we do have some geophysics database. If you want to download the subsurface database as of July 2023, it's 268 megabyte right now. And we do have a growing shear wave database. They are also complementary to subsurface database, and they can be relational, and correlations can be done over here. So next, we like to get some liquefaction potential map and studies, and high resolution Nearby soil seismic classification maps, and improve the depth to bedrock map. And if we do have time, I can show that the portal. But however, I put the portal address, and then if you go to portal and you have the subsurface geology, and you highlight this, and then you can click on any of these and zoom in, click on any of these points, and they are the borehole points, and you will get the a report linked, and then you will get the a summary plot, and it's done. If you want to do, if you don't have the capacity of the GIS capacity or other things, and you can do from the portal quite a bit the stuff you need. All right, thank you. And so for questions, you can shoot me emails, and or I can take the questions now.
Thank you so much. We do already have a question for you from Emily Brodsky. Can you tell us more about the USGS data preservation program?
I am, so we do have a data preservation group. Is the Ashley, our work group, Ashley Kebabi, is the person to contact, and Daniel Angord, also another, is the person behind this actual GIS design. So he initiated, he moved to tsunami modeling. So I moved to this, and so we exchanged time to time and groups. So the data preservation, the Ashley coordinates all of those stuff. So, and then I only provide the subsurface data and then lead the subsurface coordinations. So I would address the Ashley's communication. I'm not going to give too details, which I don't know yet. But data preservation is long years supporting light money for preserving data in Washington and other states. There are Earth MRI projects and all others. So all I am familiar is the subsurface database.
Thank you very much. We still have a little bit of time for questions. So if you have any more questions for Ray, please put them in the chat or use the Q&A feature. In the meantime, we do actually have a question that came in for Reed from the previous talk. So Reed, if you're still there, this is from Emily Brodsky. In the optimal case, what archive would work for these data?
Okay, looks like it's working. Yeah, that's a good question. I think in the kind of optimal situation would be something kind of analogous to other kinds of geodetic data where there's the more raw observations, which in the case of the tide gauge data for these historic observations might be just the scanned images of the data recordings. And then, also the subsidiary analyses, digitized time series of water levels and a hourly basis if that's what you have, or digitized for some of the merograms. Other groups have digitized those and then recorded those. So I think having kind of these multiple levels, because for many of the historic data, there's not necessarily a simple answer for how the datum was maintained through time. And so there's some assumptions that go into reconstructing the time series in some cases. So I don't know that it's the sort of thing that like someone does a reanalysis and then that's going to be the definitive thing, right answer going forward necessarily. So I think maintaining some kind of broader archive of the whole, all the data that have been collected for a tide gauge would be really great. So, I don't know who the best steward would be for that. Certainly NOAA does a lot of archiving and data distribution, but I think it's a challenge for them as well. And it's a challenge for researchers, going into the broader NOAA archives, because they just have such a huge volume from all over the place with all sorts of different kinds. So yeah, I think it's challenging. And if, people have creative ideas or know of good matches for this sort of data set, it would be great to talk to you and get your thoughts.
Thank you very much. I'm not currently seeing any more questions. So just as a reminder, if anyone has any questions during any of the talks, you can use the chat or the Q&A feature. And without further ado, I think we will move on to Dr. Sarah Ogburn's presentation. Dr. Ogburn is a volcanologist with the U.S. Geological Survey / USAID Volcanic Disaster Assistance Program. She develops and analyzes databases to help with eruption forecasts. So without further ado, Sarah, the floor is yours.
Great. Can you see my screen?
Yes, we can. Thank you.
Great. Let me just get going here. First of all, thank you so much for having me. I think my talk might be a little bit of an oddball, so I thank you for having me. I'm going to talk about eruption chronology data for forecasting and some of the challenges that we have in that realm. So first of all, let me just explain what I mean by eruption chronologies. For this talk, I'm talking about pre, intra, and post-eruption or unrest chronologies. So these are actually, they're time series data, but they're the sort of observational record rather than instrumental monitoring records. I'm talking about individual explosions, plumes, dome growth, lava flows, pyroclastic flows, sort of operational data like alert level changes or failures of instrumentation like webcams, sort of unrest observations like crater lake changes or summit cracking, as well as properties of those events. So like the heights of those columns or volumes, extrusion rates. Often we're also just trying to get counts of events where there's not really any other information. So there might not be descriptions of these events. And we are also interested in sort of qualitative monitoring data changes. So a lot of our sources might say something like there was an increase in volcanotectonic earthquakes on this day, but we're not really talking about monitoring data, instrumental monitoring data like seismic data or GPS. To give a little bit of context about the eruption forecasting part of this talk, I thought I would just introduce VDAP quickly for those that might not know who we are. So we're the Volcano Disaster Assistance Program, which is jointly funded by USGS and USAID. And we're an internationally focused volcano crisis response team. We deploy equipment, so we might deploy seismometers where a partner country needs it. And we respond to crises. That's both on site, where we might travel to a volcano having unrest or an eruption, but increasingly remotely these days. So this includes in donating and installing equipment, providing satellite remote sensing data, giving advice, and my sort of part of this whole team is assisting with forecasting eruptions. We also do a lot of other things like capacity building through workshops or technology transfer. And we also serve as the kind of volcano hazards expertise for the US government. VDAP has been around since 1986, and our team members have responded to more than 70 volcanic crises at more than 50 volcanoes around the world. To do this sort of eruption forecasting, we often use these things called event trees, which is just a way to sort of graphically lay out all of the possible scenarios that we think could occur during an eruption. So these event trees might start with unrest, whether that unrest is magmatic or maybe not. If the magmatic unrest leads to an eruption or not, how big that eruption might be, what sort of hazards the eruption might produce, where those hazards might go. And this is really just a way to kind of lay out the possible scenarios so that we can work through it in kind of a logical and systematic way. The data that we use for eruption forecasting is pretty varied. We don't have any kind of prescriptive way of doing this. There's no plug and play way to forecast eruptions. So we're using a lot of different data. We're using monitoring data and eruptive histories. We're doing global statistical analysis on the data sets we have. We've got our sort of conceptual models, and we have physical models of different processes. So a lot of times when we're trying to help a partner, we're working with our partners to do some forecasting, we have these really common questions that almost always come up. How often does unrest lead to eruption? How long after the eruption starts do the biggest explosions happen? What's the sort of volume partitioning between an eruptive column and the pyroclastic flows it might produce? And so to answer these questions, I've built this database that we call ECHRON, Eruption Chronology Database, and I'm populating it with really detailed eruption chronologies. From literature, from observatory reports, I populate real-time chronologies while we're responding to a crisis, and I ingest a lot of other data sets that have useful information. Right now, there's about 16,000 events in the database, and right now it's mostly focused on dome-forming eruptions as kind of a starting point. And it's designed to connect with many other databases. So we use this database, along others, to visualize timelines of event data alongside the instrumental monitoring data, to inform our conceptual models, to come up with analogs to the unrest that we're looking at the moment. We're often using it to fill in gaps where there's little local knowledge at the particular volcano. We use the database to derive model input parameters. So these might be geophysical models of, say, tephra distribution or pyroclastic flows. And we do a lot of analyzing of global statistical trends. I'll just show you some quick examples of what these eruption chronologies might look like. This is one for readout, where you can see that there's instrumental monitoring data plotted alongside a lot of these sort of observational events down at the bottom. I'll go through these kind of quickly. Here's about 300 years at Merapi. This is basically all event data, different sizes of explosions, different types of events, extrusion rates, dome volume, etc. Another for Bezimiani in Russia, Santa Maria in Guatemala. Here's one that we did in real time for the eruption at Agung in Indonesia in 2017. You can see that there's lots of instrumental monitoring data plotted alongside this more observational type of stuff, which helped us kind of get a holistic view of everything that was going on in sort of this one view as we were responding to the eruption. And as we were responding, we were often trying to look back at previous eruptions of Agung. So here's a really basic sort of timeline that we had for 1963. Well, a basic visualization of such a timeline, where we're trying to look at past eruptions of Agung and how those eruptions progressed. So we have a lot of good information for 1963. Agung doesn't have that many eruptions to look at. So we were really interested in what happened in 1843 and 1710. And I'll come back to that in just a moment. So what's the problem? Databases of eruption level data exist. There's not really event level data other than a few topical databases. And while global data for monitoring data is becoming more accessible, like WOVODAT, as you heard, most volcano observatories are not currently keeping digital eruption chronologies. And those that do still usually just publish these in narrative formats. And while there's tons of accounts of eruptions in the literature, even modern publications rarely digitize these event chronologies or even publish kind of easily digitizable tables. So I'll just give you some examples of the kind of sources that we're working from. Of course, there's ancient eruptions that are known only from their deposits. It turns out they're very rarely ever labeled so nicely in the field. And so this is a whole rabbit hole I won't even get into because of all of the issues trying to get this kind of information. Going back to that Agung example, though, when we were trying to find information for the 1710 eruption, it turns out Indonesia keeps really amazing records. It's just a matter of trying to interpret them. So I won't read this out loud, but you can kind of see this first paragraph is all this kind of date information. You know, the fourth month, the third year, the third decade. And there's also a lot of great chronology information in here. It's a little bit disguised in this poetic language. As shattered was the sky, as crushed was the earth. But if you read through this, you see information about pebble-sized ejecta and evacuation, ballistics, property damage, etc. And it turns out there is some really amazing work done to figure out what all of this timing stuff is so that you can put together a chronology. I'll just go through some other examples of this sort of source material, going to some more modern examples. This is some of the work by volcanologists for the Mount Pelée eruption. We've got great drawings and notebooks and more recent interpretations of those notebooks that also include great graphs. The red is plotting cumulative dome volume. You can see how difficult that would be to try and digitize. We have essentially printed databases. So this is Unrest at Large Calderas of the World by Chris Newhall. And the way that this was presented is in these kind of tables with this coding that means something. This is actually something I have already gone through and digitized the whole thing, but it's definitely time consuming. And we obviously have more modern observatory reports and literature. And one thing I want to point off right off the bat here is that the purpose of, say, observatory information statements and other types of reporting is to communicate that important information to the public in the language of that audience. And the primary purpose is definitely not to make my life easier. So this is not a complaint about the kind of content that is included in these. But this is just to show that a lot of observatory reports are in the kind of a narrative format that takes sort of careful parsing out with a lot of knowledge of particular translations of types of events that can get completely muddled by any translation services you use. They often have counts and dates of things. And they do often have tables of events or graphs of events that are pretty easily digitizable. Oops. So how do you archive this eruption chronology data that span from geologic history to modern observatory reports? Well, we've taken a few tacks with this. One is just really flexible database design. Another is ingesting as many data sets as we can that are pretty automated in a way, so like volcanic ash advisories. We're trying to facilitate now a project that will help kind of promote digital eruption chronology keeping at observatories. And that is part of this new VDAP and Global Volcanism Program Daily Volcanic Activity Report project, which I'll tell you about in just a moment. So in terms of flexible database design, this includes really granular referencing of all the events and properties. There's fields for storing that exact original text so we can come back to it later and with a more critical eye towards what was going on. There's lots of codes for recording date and time types, the date methods, uncertainties in those dates. We have a sequence field that lets us put things in order when the sort of timeline is known, but the dates of events aren't known. And we can record alternative event types when the original sources aren't clear. It's not clear exactly what type of flow that was, so we can record both. And we can rank different property values when there's multiple values that exist in the literature. So many of you know if there's some kind of explosion, there will be 10 different papers giving 10 different volumes for that eruption. I'll just show you a few examples of some of my tables that I use for dates. Often in narrative reports, you'll get things that say late 1953, and I have codes and ways of turning that into actual dates so that we can kind of do queries on that, but we still retain the kind of knowledge of what sort of date that was. The same with times. I have all of these tables that will convert things like late morning into a time that we can actually do math on. Ways to take pretty vague numbers and turn them into something that we can compare to other data. Really detailed tables of event types and how those might have been called in older literature or in other countries, or just other phrases that mean the same thing. Like I said, we're trying to ingest as much automated data as we can. It's pretty easy to automate some data extraction from a volcanic ash advisory because they give the volcano, the time that ash was observed, the flight level, which can be converted into meters above sea level, and some other things that can be pretty much automated out of these text reports that have a standard format. And finally, I just want to mention some of the new projects that we're doing. This is kind of an idealized schematic of how observatories could start keeping more digitized event chronologies. Primary observations could be made by observatory staff so that not a lot of additional work is placed onto them. And then chronology forms could be filled in by a dedicated chronology keeper, or more event data could be collected in some of the existing reporting systems. That goes into the database, which powers a whole lot of different possibilities of, dashboards for those observatories, search tools, as well as helping us answer some of these forecasting questions with global data. And just a final plug for the Daily Volcanic Activity Report. This is, like I said, a new project between VDAP and the Smithsonian's Global Volcanism Program, with the idea that we are using existing observatory reports to extract event data and to write a little narrative summary of that data. This is being done by a few new hires. We're also hoping that observatories will contribute their event chronologies, and we have a few kind of test cases going with that. Like I said, we're ingesting any kind of other data as we can. And then with that database, we are hoping to, we'll have that data publicly available on the GVP website, the event data and those narratives. It will also serve as an archive for that observatory partner data, a sort of backup of all of that isn't on their servers. Like I said, it helps with that eruption forecasting and support from VDAP. And there's other users as well. So there's a lot of interest from sort of government sectors for situational awareness and other places. And then we hope it will help other existing databases like the WOVODAT database. We can always use volunteer help. There's no shortage of stuff that I would love to get into the database. So if you know of anybody who would just love to do a ton of data entry, let me know. And I'll just end there. Thank you very much.
Thank you so much, Sarah. Let's give a couple minutes for anyone who might have questions. Please feel free to use the chat and/or Q&A function. Emily has two questions for Sarah. One, how does the research community access eChron?
Yeah, so we're exploring a few different ways for this. One of the things is that our team does not really have a ton of computer scientist support to work on front ends for this. And so we're hoping that a lot of the kind of community access will be through the GVP website. And potentially some of this would be available through the WOVODAT website as well. It's something that we're working on and thinking a lot about, but we're just a little bit too early to have like a nice front end where it's all searchable. I think that should be coming in at least some formats within the next year. But anybody is always welcome to just reach out directly to me. It's the kind of thing I do for a lot of people who know about what I've got, and so can just do queries to help out.
Thanks. And then we have a second question from Emily, and that's, is there any ways that SZ4D can help you get volunteers? We have a mailing list as well as other resources.
Yeah, absolutely. That would be fantastic. It's one of the difficulties, this being a USGS project, I don't have a pool of student minions to work on this. And most people who reach out to USGS wanting to volunteer want to go do something cool on a volcano. So it can be pretty challenging. I'd be happy to write up a kind of description of the work if it's possible for you to distribute that. Yeah, that would be great.
That'd be fantastic. Okay, I don't see any more questions. So I think in the interest of time, we will move on to our next presenter. So that is David Essing. David Essing obtained his PhD at ISTER Grenoble and is now a postdoc at Ruhr-University Bochum. While he did his PhD on crustal seismicity in extensional environments, he is now very interested in subduction zone seismicity. Thank you for joining us, David. And without further ado, the floor is yours.
Perfect. I hope you can hear me.
Yes.
Thank you very much, first of all, for setting up this very interesting meeting. I enjoyed it very much so far. Today, I'm going to talk about or introduce the community a bit to unarchived data from large-scale seismic deployments that were conducted when I was still at school, so some 20 years ago, 25 years ago. You see here a bunch of names, all of them were involved in these projects, and I am just the postdoc now presenting this, but the real work was done by those people which were back in the days at Ruhr-University in Bochum and are nowadays all over the place at different institutes. So let me just briefly introduce you, as you might all come from the Americas. Let me introduce you to the Hellenic subducting system. So we are here in the Mediterranean, first of all. You can see the red frame. That's basically Greece and Turkey to the east. And this is where we are placed. And as Europeans, we are quite interested in this relatively small subduction zone. That is the subduction zone where the African plate subducts basically beneath the Aegean Sea. We can see here kind of a tectonic sketch. And it's in many ways a very interesting subduction system. It subducts at a very relatively high velocity or high rate. But on the same time, it does not produce too many large earthquakes. So it's assumed that it's mainly aseismic happening. However, there were some large earthquakes reported in historic data. So there is this magnitude 8.3 that occurred here in 365. And some 1,000 years later, there was another magnitude 8 event occurring somewhere here. This is all kind of west or south to Crete. And that makes it obviously very of large interest to the European communities that live close to the Mediterranean coastlines, because especially this magnitude 8.3 earthquake here that produced a large tsunami that was felt all around the Eastern Mediterranean. To better understand this whole system, there is lots of research going on nowadays, but also some years ago, and I can now introduce you to the experiments that were conducted back in the days by the Ruhr-University and collaborators. We see here different networks that were deployed, starting with the yellowish one. You can see the timeline here. That was a 1 or 3 component short period experiments. Here, several were conducted during the 90s and early 20s. And you can then see that other experiments were conducted, moving more and more to broadband stations, also including ocean bottom seismometers. You can see here the SciNet and LibNet deployments that were placed here for some time periods. And later on, the Egelados experiment. That was a very large-scale experiment, an amphibian experiment. In fact, you can see here all the stations are placed on mainland Greece or Peloponnese, for example, Crete, and on these small islands. But we can also see that lots of seismometers were placed on the ocean bottom or the bottom of the Mediterranean Sea. These were ocean bottom seismometers. I will give some more details about this experiment later on, because there is some data still not available yet. The end of this large-scale funding scheme that came from the German government was a Nisiros experiment that was then here conducted in the eastern part of the study area, then from 2006 to 2012, more or less. So while most of the data is publicly available via geophone here indicated down right, there are still some data which are not publicly available, but still of large interest, we think. And therefore, I'm going to introduce you now to the unarchived data from the Egelados dataset. So once again, that was this amphibian experiment. Seismicity was, or stations were placed on land, but also offshore. There were some problems. It was the first time large OBS deployment was conducted, and there were some problems with the ocean bottom seismometers. Unfortunately, they were not recording during this 1-year period where they were placed there. However, there were, at the frame of each ocean bottom seismometer, there was a hydrophone attached. And these hydrophone data are quite useful, we found recently. We looked into the waveforms, and we can see here the waveforms of land stations, and marked or framed in orange. These are data from hydrophones, and you can see that even when we have obviously difficulties to define an S-peak of an earthquake. For P-picking, these hydrophone data can be very, very important and can give us thereby then additional information, especially if we want to better constrain the location of seismicity that we detect. There was some work done with these hydrophone data already. For example, Andrea Brüstler in 2012 worked on finding a planing and velocity model. But there's still a lot of things to do, especially here in the western part. These hydrophone data were for now not pretty much explored. So we want to make them publicly available soonish. They are still not publicly available because there were back in the days also with the hydrophones some small issues. For example, there was on some stations a little time drift where we had trouble to report them on the online archives. But now with some new versions of metadata, we can report these time drifts and will make them publicly available soonish. Another experiment that was also conducted in this time period in the 2000s was this small scale arrays here in southern or in Crete, basically. And just to build the bridge back to my little introduction slide, we had these magnitude 8.3 that occurred southwest to Crete somewhere. The location is, for obvious reasons, not very clear. However, this experiment here, this network was placed exactly at the place close by where we assume the earthquake rupture in 365 to have happened somewhere. So this can be used to study the area. And also here, while there were some studies, small-scale studies already done, these legacy data can be still of interest, especially with nowadays automatic picking algorithms that can facilitate the picking of earthquakes. And therefore, we think that these data sets are very valuable. There is another data set from a small-scale array here in the southern part, which can also be of interest. However, you can see on the right side, they are not on a server yet, but on these disks so far. We recently discovered them, and we want to make them publicly available also soonish. But yeah, that's we already indicated that it's time consuming doing these archiving tasks, and time is rare. So if anyone is interested in having the data right now, you can easily reach out to me or to the colleagues I mentioned at the beginning of the talk. So feel free to reach out to me if you have any questions. Here, that's just my conclusion in the summary. And here are the data set that are already publicly available, which I indicated at the beginning of the talk. And if you are then interested in the data which is not publicly available yet, and you have urgent need of exploring this data, we are very happy if you reach out to us, and we will find a way how to share the data immediately with you. Yeah, that's it from my side already, and thank you for being here.
Thank you very much. We already have a question for you from Tim Ahern, who says, hydrophone data can easily be managed by FDSN seismic data centers, of which GFZ is a very capable center. Have you approached GFZ about archiving these hydrophone data?
So we are aware of that, and we want to make it publicly available exactly there. It was only that when they first wanted to make the data available for public back in 2000, in the early, not 20 years ago or what, it was a bit difficult to report the time drift that is on some of the stations, and therefore it was back in the days not done. But yeah, we will definitely do it via them, because I guess that's really the way to go. They do a great job there.
Great, thank you. I'm not seeing any other questions for you at this time. So just a reminder to everyone about the Q&A function and the chat, and there'll be time at the end of the session, I'm seeing a question from Christos Evangelitis. If you ever have any issues on staging the data, Ada at NOAA could always host these data. Sorry, not a question, more of a comment. But thank you, Christos, for that comment. Without further ado, I think we will move on to our final presentation of this session. And then there'll be time at the end for questions for both our next speaker and all of our speakers. So our next presenter is Heather DeShon. Professor Heather DeShon is an earthquake seismologist at Southern Methodist University. She specializes in high-resolution earthquake location and tomographic imaging with application to subduction zone processes and natural and induced intraplate earthquakes. Thank you so much for joining us, and without further ado, the floor is yours.
Thank you. So I'm going to piggyback off of some of the themes from the most recent speaker. I am presenting some legacy ocean bottom seismic data that was collected offshore Costa Rica as part of the NSF Margins CRSEIZE data set. The data was collected in 1999 and the OBS data into the year 2000. The land
Sorry, Heather, you're not in presentation mode.
You're not, I'm not in present. So what do you mean? What are you seeing?
Could you click
There's
swap
some-
displays?
Yeah.
Oh, you need me to swap displays. Yeah. Where's that at?
Top left.
Here, let's just do this. Sorry, on my double screen, it looked like it was all fine. You're still.
We're still seeing the presenter view.
Yes, I see that. I'm gonna stop share just a second. That's where did you go? Sorry, now I've lost my Zoom screen. Good Lord, you wouldn't know that I do this every day. Zoom screen. All right, there I am. Sorry, I lost myself for a minute.
No worries.
I need to, gosh. Is that better?
Perfect.
All right, sorry about that. Good
No
thing that
worries.
the other speakers were a bit ahead of time. Anyway, thank you for having me, and I'm going to be presenting on some OBS data off of Costa Rica. Now, the data that I'm presenting today were funded by the Office of Naval Research, so they're called the ONR OBS out of Scripps. They were under the guidance of Leroy Dorman, who passed away earlier this year. So in my title slide, you would have seen that this talk is a bit in memoriam. This is Leroy, and he's standing in front of the OBS that I'll be talking about today. So if you had the pleasure of interacting with him at some point in his career, I know you probably think as fondly of him as I do. All right. So offshore Costa Rica and Nicaragua in the late 90s, early 2000 time period, both the National Science Foundation's Margins program and German SFB funding mechanism were serving to fund both a wide range of marine geophysics experiments. So this is a figure that was captured in the 2008 time period, just kind of showing both land seismometers, also, let me get my, never mind, showing the land seismometers, the wide angle reflection experiments, swath bathymetry, and included in this are some OBS. So I'm going to concentrate on the US ocean bottom seismometers, but there were also a large collection of German OBS and OBH experiments that went on during this time period. Oh, and I should say, none of this work would have been possible without significant collaborations by both Costa Rican and Nicaraguan scientists. All right, so this is just focusing on the seismic networks of Costa Rica and Nicaragua, as captured again in the kind of early 2000 time period. There were a couple of ODP drill sites in this area. There was a 3D seismic survey off of the Osa Peninsula. So if you are familiar with Costa Rica, the southernmost peninsula is the Osa Peninsula, the northernmost peninsula that sits out over the Middle America Trench is the Nicoya Peninsula. And you can see with the circles, the collection of offshore instrumentation. So the NSF OBS experiments took place off of the Osa Peninsula, just to the north of the Osa Peninsula, and then off of the Nicoya Peninsula. And then the German OBS experiments took place off of Nicaragua and then in between the two NSF experiments. And then there was also land stations in both onshore, offshore experiments by the NSF and the German groups, and then also the two countrywide seismic networks in Costa Rica and the countrywide seismic network in Nicaragua. So various parts of these data sets are publicly available. So again, to concentrate on the National Science Foundation experiments, these were called the CRSEIZE experiments. They were to Susan Schwartz at UC Santa Cruz, to Tim Dixon at the University of Miami, and to Leroy at Scripps, with involvement with German collaborators and also Marino Protes group down in Costa Rica. The OSA experiment ran first, so that's the southernmost experiment. The OBS that successfully collected data are shown by the solid squares. The open squares are instruments that were recovered but did not have usable data. And so there were a combination of land seismometers and OBS, and they recorded for 2 months an aftershock sequence of a magnitude 6.9 earthquake that occurred in late 1999. So there were 18 stations in total, about 1,500 earthquakes on this data set, a little over 10,000 P waves and almost 10,000 S wave arrivals. The Nicoya Peninsula experiment was a bit longer. The OBS component was 6 months long, from late 1999 to mid 2000. There were also land stations and geodetic stations associated with this experiment that operated into 2001. There were 33 experiments total, well over 10,000 earthquakes. The experiment recorded an outer rise earthquake that generated a large aftershock sequence that was just outside of the network's coverage, so that can dominate the data set. For this experiment, over the years and last reported in this paper by Moore Driscoll and BSSA in 2013, there's about 152,000 P wave arrivals and almost 78,000 S wave arrivals. Neither of these data sets have gone through any sort of modern machine learning or deep learning detection and association, though I do have a student working on that right now. The land data for these experiments is all archived with the EarthScope DMC. The OBS data is not archived with the DMC. And in fact, the reason I'm giving this talk is to beg someone who might happen to be listening to help me or to take the existing SAC and mini-seed files and archive this data with the EarthScope DMC. And you'll see in a minute why it's not archived with the DMC. Okay, so this was the very last experiment for the Scripps ONR OBS, right? This was prior to the creation of the current version of the US OBS instrument pool. At the time, there were 14 of these OBS. They had an exterior frame anchor assembly, right? They worked on flotation by glass balls. Some of the sensors would hang off the side with a rotating arm pivot. Some of the sensor packages were directly connected to the frame. Half of the sensors were precision measurement device broadbands with an instrument response file. Half of the OBS were actually gimbaled marked product L4C triaxial 1 Hertz geophones, and each channel of those had a unique instrument response. And if my memory is correct from when I was a newbie graduate student, it's that fact that was keeping that and some post-processing for clock time that kept this data set from being archivable with what was then the IRIS DMC in full seed format, the different response per channel issue. Some of the instruments had hydrophones. Interestingly, I actually don't remember if we had hydrophone data. If we did, it certainly never came to me as a graduate student. And then I have been carrying around this data set for 20 years. All right, so you can always ask me for the data and I'll send it to you, but it's not archived. Post-processing for this CRSEIZE data occurred at SIO, including the calculation of instrument response, clock corrections. And again, I carry a copy of this data in seed or SAC format. If you want to kick it old school, it was sampled at 64 samples per second or 128 samples per second. It should have 120 dB dynamic range. The clocks performed really well. My dissertation actually contains clock drift information, and we saw only one station that had significant clock drift. There were also this really unique locking compasses on these instruments, and I also rotated them as part of my dissertation. So there's some additional metadata that can be made available for this data set. The data quality was pretty good. I mean, it was noisy because it's OBS data and it's early 2000, late 1990 era OBS data. Here's just a couple of waveforms off of OSA. If you look, SS17 was one of these L4C sensors. Why I got away with only showing 2 out of 3 channels in my dissertation, one cannot remember. Similarly, there's a nice local earthquake recorded on the bottom of this slide on the PMD sensor, right? So it's really nice data. The Nicoya data, again, was 6 months. Some of the land stations are shown on the left, but here you have 2 of the L4C sensors. Again, why I didn't plot a PMD example in my dissertation, I do not know, but it is what it is. They were noisy, or I mean, they were nice, but it was a bit noisy. And again, these OBS did capture. I think we pulled the OBS right before that outer rise earthquake happened. That's one of the problems with the experiment. We did some interesting work with these data. We extracted the noise spectrum, removed the tidal signature and things like that. The Nicoya experiment had co-located fluid flux meters out of Brown's group at Scripps at the time. And so we could see how the noise level on the OBS actually increased and reddened during the time of fluid fluxing out of the toe of the prism. We never did a similar analysis with the OSA data, as the fluid flux meters were not co-located with that data set. But it's probably an underutilized OBS data set. in a margin that has a really rich history of geophysics data that could be integrated with it now. And you know, we pulled the cream off for the early 2000s, right? We did earthquake catalogs, myself and Andy Newman, who's now at Georgia Tech. There's phase catalogs for this data. There's differential times and cross-correlation based differential times from this data set that could be made available. There's derived 1D and one Nicoya Peninsula 3D velocity model and an attenuation model. There's stress drops for some of these earthquakes. And then the geodetic land data, along with the land data, is available through EarthScope, right? And the Nicoya area itself had continued operations from Georgia Tech and Officicori and UC Santa Cruz for any number of years after the OBS were pulled. So again, you know, the purpose of giving this talk was to remind everybody that the OBS off of Costa Rica were put out in the early 2000s. That data can be made available, and I'm happy to collaborate, and Susan also is happy to collaborate with anyone that would help us figure out how to get the data into the EarthScope DMC, because I believe that the flexibility of the metadata has changed since we were told we couldn't do it in the early 2000s. So Susan couldn't be here today, so special thanks to Susan. And of course, no marine geophysics talk is final until the shipboard group is shown. So this is the shipboard group on the German Sonne vessel in 1999. Thanks.
Thank you so much. That was a great talk. Please feel free, everyone, to send in your questions for either Heather or all of the various speakers from the past hour and a half. Tim Ahern did say that IRIS and EarthScope DMC should have no problems, different responses per channel. That would have been true at any time. There must be some other problem. And Jerry reiterated that you should please contact him about the OBS data that you want to archive. Work is progressing on capturing OGS clock drift in seed data.
Yeah, it might have just been the clock drift that was the issue.
So we have 3 more minutes for questions. If anyone have any, if you think of something later, please feel free to contact us at contact@SZ4D.org. And as a reminder, all of these talks will be uploaded to the SZ4D YouTube channel later today. If you want to rewatch or if you want to send them to your colleagues or other network participants. I will give us a few more minutes just in case people are typing out more questions. We have a question from Helen for Heather and David. Are you aware of any other similar marine deployments that may have encountered these archival challenges previously that would be worth revisiting now?
So my guess is, and you know, maybe Tim can correct me, my guess is a lot of the OBS work done with those ONR instruments at Scripps is not archived. Actually, I think Doug Weens used that a lot early in his career, so he might have insight into that. And then that German OBS, OBH data, I don't have, I mean, I have copy of it, but I don't have permission to share it. So how the Geomar OBS and OBH have been archived, I can't say.
Yeah, for the German side, I would say that especially the broadband seismometer that then were used more often after this large-scale experiment were then better and better archived at the Alfred Wegener Institute, probably. I would guess that most of them are archived, but people at Alfred Wegener Institute should be aware of that.
Thank you. I don't see any more questions, and we're rapidly approaching the top of the hour. So I want to thank all of our panelists this session for their amazing talks and for contributing to this virtual workshop. And I hope we will see everybody tomorrow at 8 a.m. Pacific time or 3 p.m. UTC. We'll be using the same link, and we'll have 2 more keynote talks at that time. Thank you so much, everyone, and have a great rest of your day.